Okay, so hello and welcome back. So in this video we want to talk about rational numbers. About rational numbers and their decimal expansion. Okay, so of course this is not from the point of view of working with rational numbers or their decimal expansions and things like that. I have actually done a few videos and courses on how to work with rational numbers and their decimal expansions and things like that. And if it's required, if it's necessary, we will go back to, I don't know, if you have any questions, you can ask your questions here. I will put together probably, I might put together a couple of videos explaining how to deal with rational numbers and the decimal expansions and so on and so forth. But basically, this video is from the point of view of basically putting together all of those results together and stating them in the form of a couple of theorems. And then we will do a couple of examples using the theorems that we do here, and then that's basically that's all about these few videos, probably 1 or 2 videos that we will do on rational numbers, at least for now. So basically, hopefully you know that that rational numbers have either a terminating decimal expansion or a non-terminating recurring. So basically the idea here is that rational numbers have either a terminating decimal expansion, or a non-terminating repeating. And this is also sometimes called a recurring. Okay, so that's called recurring. So what that means is that, for example, let's say for example, let's have, for example, some number like 0.375. This number 0.375, you can write it as 375,000th. Okay, and that's a rational number. Of course, you can simplify this to, I don't know, we will get to some stages where we will simplify a couple of these, but just for the sake of this discussion, you know that 375 divided by to 1,000 is equal to 0.375, and 0.375 is the decimal expansion of this rational number. This rational number is in the form p by q, where q is not equal to 0, and the decimal expansion of this number is terminating, because the numbers, if you actually do this calculation, this division, you will basically the division will terminate in a 5. So that's basically what we have in the case of terminating decimal expansion. On the other hand, there are some numbers that that do not terminate. For example, let's say a good example for that is, for example, 1/7. 1/7 is a rational number. Okay, 1/7 is a rational number, but if you try to represent it or express it in a basically, if you try to write it in this form, in a the decimal representation of the number, what you would get is that, for example, you have 1 divided by 7, and then you have here, you will have a 0.0. Actually, this is supposed to be a, so 1 times 7 is equal to 7. You have a remainder 3. And then if you have a 0 over here, 0, so then you will have 4 times 7 is equal to 28. You have a remainder 2, 0, 0. You have a 2 times 7 is equal to 14. You have a remainder 6, 0, 0. You have a remainder 7, 8. 8 times 7 is equal to 56. You have a remainder 4. If you have another 0 over here, you will have 6. 5 times 7 is equal to 35. You have a remainder 5. And 7 times 7 is equal to 49. Remainder 1. And you got back to remainder 1. So you saw over here that the remainder was here. I had the 3 over here, I had the 2 over here, a 6, a 4, a 5, and then basically the number that I started with was basically a 1. So I have a 1 over here, and I have the 1 back over here. Now if I go back here and add a 0, and add the 0 back over here, I'll have basically 1 times 7 is equal to 7, and I have a remainder 3. So you see the same, the remainder 3 basically appeared here again. If I add a 0 over here, what I will have is basically 4 times 7 is equal to 28, and that's a 2, and that's again the remainder 2 that I had here. So you see these remainders are actually repeating themselves again over and over again, meaning that the remainders that I have are 3, 2, 6, 4, 3, 2, 6, 4, 5, and 1. And then again the same thing happens again. So you have again a 3, you have again a 3, 2, 6, 4, 5, 1, and so on and so forth. So this block of remainders is going to repeat itself if you keep doing the same operation. 3, 2, 6, 4, 1, 3, 2, 6, 4, 3, 2, 6, 4, 5, 1, and so on and so forth. And for the same reason, if you do this calculation, this block of numbers over here, 1, 4, 2, 8, 5, 7, 1, is going to repeat up to 7, meaning 0.142857 is going to repeat itself over and over again. As you can see already, we have 142857, 142857, 142, and so on and so forth. It's going to be, and that's basically called recurring, meaning that if I were to write the decimal expansion of 1/7, I would simply write it as 0.142857 recurring, and we put a bar above these numbers, meaning that this block of numbers recur and basically repeats itself over and over again. So that's the meaning of non-terminating repeating, or basically we call that also recurring. So again, a rational number, whatever that might be, can have two types of decimal representations. One type of decimal representation is that it can be terminating. For example, in the case of 375 to 1000. 375 to 1000 is going to be 0.375, and it terminates. So it's a terminating decimal expansion. On the other hand, for example, 1/7, as you saw over here, is going to be equal to 0.142857, and then this block of numbers is going to repeat itself over and over again. So it's called non-terminating non-terminating repeating or recurring. So, and hopefully you have worked with these numbers. I mean, that you have, already well how to represent rational numbers, how to basically express rational numbers in terms of their decimal representation. Again, if you have any problems there, we could probably do a couple of videos on how to do that. It's all about, it's mostly about basically working with numbers, playing with numbers, the prime factorization of numbers, simplification, and things like that. There is nothing much complicated there. Okay, so now what we want to do here is that basically we want to consider a rational number p by q. We want to consider a rational number p by q, basically q not equal to 0, and we want to explore exactly when the decimal representation of this number is going to be terminating, and when it's going to be either terminating the decimal representation when it's going to be terminating, and under what circumstances it's going to be terminating, and under what circumstances it's going to be non-terminating repeating. And then that way we will basically know our numbers much better, and then we will be able to work with them much more, much more fluently, you could say. So, so now as a couple of examples to show you some patterns over here. So let's consider a couple of rational numbers. So let's say that you have 0.375. Let's say that you have, for example, 0.104. Let's say that you have 0.0875. And let's say that you have 23 for example, 3408. Okay, so these numbers, of course, you can write them in basically 0.375. 0.375, you can write it as 375 thousandths. Okay, and also these numbers have this, basically this is the same story for these numbers, meaning that this number can be written as 104 thousandth, this number can be written as 875 ten thousandth, and this number can be written as 233,408 ten thousandth. Okay, so now if I start with this number and try to simplify this number. Now I got 0.375 is the same thing as 375 to 1000, right? So now 1000 is the same thing as 10 raised to the power 3, as you already know that. And 375 is divisible by 5, as you know, so it's also divisible by 3, but I suppose you can start with 3 as well. So for example, if you prime factorize this number, you'll get 375, and it's divisible. 12 plus 3 is equal to 15, so it's divisible by 3. Now 375, if you divide it by 3, what you'll get? 1 times 3 is equal to 0, 2 times 3 is equal to 6, 15, 5 times 3 is equal to 15, 0. So it's 3 times 125. And this is not divisible by 3 anymore, so you can divide it by a 5. So 125 divided by a 5, I think it's 25. So 2 times 5 is equal to 10, 25. 5 times 5 is equal to 25, so that's 5 times 25, and that's 5 times 5. So that's 5 cubed times 3. So that's 3 times 5 cubed. Okay. Now, what you can do here, is you can write this number as so 3 times 5 cubed, and then you can write this as 2 times 5. The prime factorization of 10 is actually nothing but 2 times 5. So 2 times 5 whole raised to the power 3. And then you will be able to write this as 3 times 5 cubed. And then you can simplify this to 2 cubed times 5 cubed. Okay, so that's basically your number. Now 5 cubed and 5 cubed you can cancel out, and you will be left with 3 over 2 cubed. 3 over 2 cubed. Okay. So that's basically, for example, your first number, 0.375. Now, the second number that you have is 104,000th. So 0.104. 0.104. And what this is, you can write it as 104, as the name suggests, as the way that you even read this number suggests that this number is 104,000th. Okay, and then you can write this as divide probably by 2. Okay, so 104 divided by 2 is equal to 51, and 51 is divisible by 13, which is equal to 4 times, I'm sorry, this is 52. And 52 must be divisible by 13. So 40 and 12, 52. Okay, so that's 4 times 13. That's 4 times 13. Actually, 4 is the same thing as 2 raised to the power 2. 2 raised to the power 2 times 13. And then 10, basically 1000 is the same thing as 10 raised to the power 3. So you can write this number as 2 raised to the power 2 times 13, and 10 raised to the power 3. You can write it as 2 times 5 whole raised to the power 3, which is equal to 2 cubed times 5 cubed. 2 cubed times 5 cubed. So 2 cubed and 2 squared you can simplify, so you'll get a 2 over here. So it's equal to 13 over 2 raised to the power 1 times 5 raised to the power 3. That's basically this number over here. Okay. Now the next number, so you need to basically, of course, we will come to some conclusion at the end of basically once we have basically worked with these four numbers. But now the next number that we have is 0.0875, and that's equal to 875 10,000. Now this is equal to 7 plus 1 to 12, 20. It's not divisible by 3, it's not divisible by 2, it's divisible by 5. So 875, if you divide it by 5, what you will get is 1 times 5 is equal to 5, 3. So 7 times 5 is equal to 35, 25, and 5 times 5 is equal to 25. So what's 175? So then 875, if you divide it by 5, you will get 175. And 175 divided by 5 is 175 divided by 5 is 2 times 3 times 5 is equal to 15 and 25, so that's a 35. So 5 times 35, and that's 5 times 7. That's 5 times 7. Okay, so that's the prime factorization of 875, and 10,000 is the same thing as 10 raised to the power 4, which is equal to 2 times 5 whole raised to the power 4, which is 2 raised to the power 4 times 5 raised to the power 4. So this is equal to 1, 2, 3, so 5 cubed into 7 over this number over here, 2 raised to the power 4 times 5 raised to the power 4. Okay. Now what happens here is that here you have 5 raised to the power 3, 5 raised to the power 4, so you can simplify this. You can write 5 raised to the power 1. So this is equal to 7 over 2 raised to the power 4 times 5 raised to the power 1. And that's basically that. So you have again so as you can see over here, already you can see a pattern over here. You have some factors of 2 in the denominator, some factors of 2, some factors of 5 in the denominator, again some factors of 2 and 5 in the denominator. And we can do this last one as well, so it's 23.3408. So if you don't know how to write this number in the form of a fraction, it's actually a very useful skill to be able to work with these numbers. And I have already done this in the form of a couple of videos. I might actually go over this over again if it's required. But before I go any further, let me take a few minutes rest. I'll be back with you with the rest of this. Okay, so about this number, so you know that if you basically, the one way to write out this number, if sometimes this can be a little bit confusing. So one way that you can write out this number in the form of a ratio of 2 numbers is that you know that 23.3408 is the same thing as 23 plus 0.3408, that you already know. And well, you don't need to do much about 23, so you can write it as it is 23, and then 0.308, 3408, you can write it as 3408 divided by 10,000, right? So now if you add these two together, just simply adding these two numbers together, you'll get the 10,000 as the LCM of these of 10,000 as 1 and 1. And then 10,000 times 23 is equal to 230,000 plus 3,408. And then when you add these two numbers together, you'll get 233,408 divided by 10,000. So basically what that means is that means that basically 23.3408 is the same thing as 233,408 divided by 10,000. And of course, you know that if you have this number over here, 233,408, the decimal point is over here in this number. So if you divide it by 10,000, you have to move this decimal place back 4 times. So 1, 2, 3, and 4 would be over here. So that's 23.3408, and that's basically that's actually 2. So that's basically your number there. Now, so now that we know basically how to convert such numbers as well, so what you want to do is basically have this number now. Now you know that 23.3408 is equal to 233,408 divided by 10,000. And again, you can simplify this number, although it might take some time to simplify it. So you have 200, so if you divide this number by 2, so if you have 233,408, if you divide this number by 2, you will get basically 200,000 would be 100,000 divided by 2, and then 30,000 would be 15,000 divided by 2, 3,000 would be 1,500, 408 would be 204, and then if you add these together, you'll get 0, 7, and then basically a 61611. So that's 116704. Again, you can divide that by 2. You can divide that by 2. You'll get for 100,000, you'll get 50,000. For 100, so 116,000. So 16,000 would be 8,000, and then 704 would be 352. 352, and then add these together, you get it 5, 5, 3, 8, and 5. So 58350. 58350. Divide this by 2, you'll get 25,000 plus 4,000 plus 150, for example, and 25, and you'll get a 5, you'll get a 7, you'll get a 1, and 9 and 2, so 29,175. 29,175 times 2, and then you have, let me actually write it the other way around, it might be confusing. So it would be 2 times 29,175, divide this number by 2, divide this number by 5, 29,175 divided by 5, what you will get is 5 times 5 is equal to 25, and 5, 1, so 9 times 5 is equal to 6 times 5, 9 times 5 is equal to 45, so that's a 6, 7, 9 times 5 is equal to, well, there's something wrong here, I suppose. There is something wrong here. So let me use my calculator. So 233,408 divided by 2 is equal to 116,704, and this divided by 2 is equal to 58,352. Oh, that's 352. That's what was wrong. That's 352. Okay. So now, if you divide this number by 2, what you will get is basically 50,000 is 25,000. 8,000 is 4,000. That's 150. And 52 is 26. So you'll get a 6 over here, you'll get a 7 there, you'll get a 1 there, you'll get a 9 and 2, 29,176. 29,176. Divide this by 2, you will get 10,000 and 4,500 and 50 and then 35, 38. So you have an 8 over there, you have an 8 over there, you have a 5 over there, you have a 4 over there and a 1. So that's 2 times 14, 588. And of course, you know, there are calculators for this kind of work, but it's also a good idea to actually play with numbers, work with numbers. You learn a whole lot about numbers if you just simply work with them. And well, I do these videos and it's supposed to be some sort of practice for me as well, and I don't have the habit of editing anything, so it's hard for anyone. I mean, it's hard for these videos to be probably of any use to anyone, because they are long and it's full of calculations and working with numbers and that sort of thing. But it might be, I mean, some people might find it interesting. Otherwise, I mean, to be frank, I don't really expect anyone to find these videos of any help to them. I don't know, let's see. So 14,588, so that is divided by 2 is 7,000, and 500 would be 250, and 88 would be 44, so that's 492 and 77244. Let me write it the other way around again. So 2 times 7244, and then that's 3,500, 122. So that's 2, that's 2, that's 6, and 3, 3622. 2 times 3622, and then that's 1,500, 311. So 118. So 18. So that's again 2 times 1811, and 9 plus 2 is equal to 11. And I suppose it might be a prime number, or it might be divisible still by 11, I suppose. I think this number is divisible by 11. So you have this number 1811, and you know that it's not divisible by 3, because 1 plus 8 is equal to 9, 9 plus 2 is equal to 11. 11 is not divisible by 3. It's not divisible by, I mean, it looks like it's, so if you were to look for divisibility for 11, I found it well, you of course you forget these. So subtract the last digit from the remaining leading truncated number if the result is divisible. So what's the subtract the last digit from the remaining leading truncated number? Of course, this is one way of testing divisibility by 11. There is another way as well. I'll sometime I'll show you that as well. But this might work as well. So if you truncate this number and take the last digit out, you'd get 181. And if you subtract the one from this number, you would get 180. and then if you truncate this number again, you'll get an 18. Okay, and subtract the 0, you'll get 18. So 18 is not divisible by 11. Now the way that you can make sure that it's not divisible by 7, or whether it's divisible by 7 or not, you have 1811. You have 1811, and you have to truncate the number. You'll get 181, and then the last digit that you got rid of, you multiply it by 2 and subtract it from this number. So 2 times 1 is equal to 2. So 181 minus 2 is equal to 179. And you can do the same thing again if you need to. So that would be 17 minus 18, which would be negative 1. So it's not divisible by 7, most probably not either. So the number might actually be a prime number. So 1811, you can test here. 1811, if you check for, is a proven prime. So 1811 cannot be simplified any further. So as you can see, you can write this number as 1, 2, 3, 4, 5, 6, 7 factors of 2 raised to the power 7 times 1811. And the denominator is 10 raised to the power 4. So you can write this as 2 raised to the power 7 times 1811. And 10 raised to the power 4 is the same thing as 2 times 5, in basically whole raised to the power 4. And then you can write that as 2 raised to the power 7 into 1811. And this you can write it as 2 raised to the power 4 times 5 raised to the power 4. 2 raised to the power 4 times 5 raised to the power 4. So then you can simplify this number as this is 1, so this is 2 raised to the power 3. And so you have 2 raised to the power 3 times 1811 over 5 raised to the power 4. So then your number over here, this number over here, I'll just simply erase all of these things. Okay, and I write this as 2 cube into 1811 over 5 raised to the power 4. So now that you have these 4 numbers, we can take a look at them. So you can see that, for example, this number, and remember that all of these numbers are the decimal representation of some rational number. You can see all rational numbers over here. You have a numerator, denominator, and so on and so forth. And these numerator denominators have no factors in common. They are co-prime numbers. Okay, because we have simplified them as much as possible. It was not simplify them any further. So these are co-primes, and your denominator is not 0. And these are both basically, at the end of the day, they are both basically integers. So what that means is that these are rational numbers. If these are rational numbers, so are these numbers. And what that means is that these are the decimal representations of some rational numbers, and these decimal representations are actually terminating because they have terminated. For example, this number has terminated at 5. This number has terminated here, here, and so on and so forth. So what that means is that if you have the decimal representation of some rational number is terminating, then that rational number has basically that rational number in the denominator has some factors of 2 and some factors of 5. And you can see over here you have basically factors of 2 here, factors of 2 and 5, 2 and 5 and 5. Either both of them or one of them, but it cannot be any other thing, or any other factor cannot go with there, for the simple reason that because your denominator is going to be either a 10 or a 100 or a 1000 or a 10,000 or 100,000 or some multiple of 10. So some multiple of 10 is going to be at the end of the day be, for example, 10 cubed, 10 or 10 raised to power 4, so on and so forth. And 10 basically in and of itself is nothing but 2 and a 5. So then the only thing that you can expect to have in the denominator is either a 2 or a 5 or both of them. So that's basically what happens here, is that if the decimal representation of some rational number is terminating, you can write that the prime factorization of the denominator is going to have only factors of 2 and factors of 5. Okay, so that's basically what that means. And of course, this result, again, like what we said about for example, the fundamental theorem of arithmetic in the previous video, this result you can use it in many different ways, in many different situations, and it all depends on you how. I'm sure you are smart. You are a smart person. Everybody is. It all depends on you how you want to use this result. Otherwise, it can be used in any way, in any possible way, really. I mean, what I mean to say is that basically these results, they seem to be boring, unimportant things so now why does it matter that, for example, that the decimal representation of the denominator of some number holds, for example, can be either 2 or 5. It's important because you can use it in many different ways, in many useful ways. So, but of course, before you can use it, you need to know it. That's basically why we do all of these things. Otherwise, yeah, they seem to be pretty. I mean, they seem to be useless work actually, but they are really not. Okay, so now let's write down this theorem formally, and then we will move on to the next thing. So So one more important thing that we can add here is that even though we have worked only with these few numbers over here, any number that whose decimal representation is terminating is again going to be the same story, because the denominator is going to be either a 10, meaning that you have one decimal place, or the denominator is going to be 100, meaning that you have 2 decimal places, or the denominator is going to be 1000, meaning you have 3 decimal places, and so on and so forth. So any rational number whose decimal representation is terminating is going to be again the same story. So that's something general about all numbers really. So basically, again, to add a little more to this, is that any real number, basically, any real number which has decimal expansion that terminates, it can be expressed as a rational number whose denominator is a power of 10, as you saw over here. And also the only prime factors of 10 are 2 and 5. So cancelling out the common factors as we did over here, cancelling out the common factors between the numerator and the denominator, we find that this real number is a rational number of the form p to q, where the prime factorization of q is of this form, meaning that you can at the end of this discussion, we can of course say that the prime factorization of, we can write this number as a ratio of two numbers p to q, as we have done over here, where basically, of course, q is not equal to 0, and the prime factorization of q is of the form 2 raised to the power m into 5 raised to the power n, or basically you can write it the other way around as well, or 2n and m. So 2 raised to the power n, for example, times 5 raised to the power m for some non-negative integers n and m. Okay. Now, if we were to write down this result formally, it would be something like this. So this result written down formally would be like this. So I think we have this. This must be the second theorem that we have done in the course of these videos. So this is basically the formal statement of this theorem. Okay, so now if I were to write this theorem, write down this in the form of formal in the form of a formal theorem, I would write it as theorem N2. I'm going to call it theorem N2, and the theorem is going to be, for example, let x be a rational number. Let x be a rational number whose decimal expansion terminates. Whose decimal expansion terminates. Then x can be expressed in the form then x can be expressed in the form p by q, where p and q are coprime, and the prime factorization of Q, and the prime factorization of Q is of the form 2 raised to the power n, for example, times 5 raised to the power m, where n, m are non-negative integers, where n and m are non-negative integers. Okay, so that's basically the whole situation that we have talked about for the last 50 minutes. That's basically the whole situation there. Now, as we have talked about, basically we have talked about converse of theorems in the basically logic in mathematics. There were a few videos that we did prior to these videos, and we talked about converse of theorems as well. So basically you want to know, for example, if we said that if P implies Q, then is it also true that Q implies P, meaning that basically is the converse of the, for example, if I take this theorem, this whole theorem as P implies Q, is it also true that Q implies P, meaning that if I have basically the whole situation over here where basically the decimal, the rational number can be expressed in the form P by Q, and the basically P and Q are co-prime, and then the prime factorization of Q is in this form 2 raised to the power n times 5 raised to the power m, where n and m are non-negative integers. If that's the case, can I say that then in that case the decimal representation or the decimal expansion of that number will terminate? And that's something that we will see in the next video, and that's going to be another theorem that we can actually make based off of this theorem. So I'll see you in the next video with the rest of this material.